notice you have seen that before, and this. In previous videos, we have covered all of these 17 formulae from mechanics, plus these 4 more. That would be in videos Physics 06 to Physics 11. And that make up about 55% of all the formulae required for CSEC examination, physics examination. So we have been looking at section B, thermal physics. We already looked at these 5 formulae in the last video, Physics 12. And now we will concentrate on Formula 6. EH is equal to MC delta theta. That could also be EH is equal to MC delta T. Difference here is you are dealing with the difference in Kelvin temperature, and over here you are dealing with the difference of Celsius temperature. Not that it make a difference, because they are the same things. We will also look at E is equal to MC and what that means. Now assume that you have a block of metal of several kilograms at 25 degrees Celsius. You heat it until its temperature increases to 26 degrees Celsius. The amount of heat energy that it takes to increase or decrease the temperature of a body by 1 degree Celsius or 1 degree Kelvin is called the heat capacity of the body. This quantity is given the symbol uppercase C and is measured in joules per degree Kelvin or joules per degree Celsius. For example, C is equal to 2.4 megajoules per degree Kelvin. Now, let us now assume that you have just 1 kilogram of that mass that we were talking about over here. The heat energy that it takes to increase the temperature of 1 kilogram of a body by 1 degree Celsius or 1 degree Kelvin is called its specific heat capacity. It is given the symbol lowercase c and is measured in joules per kilogram per degree Kelvin or joules per kilogram per degree Celsius. For example, you may be told that for water, its specific heat capacity, that is lowercase c, is 4,200 joules per kilogram per degree Celsius. That means that it takes 4,200 joules of heat energy to increase the temperature of 1 kilogram of water by 1 degree Celsius, or you could say 4,200 joules of energy has to be removed from 1 kilogram of water to lower its temperature by 1 degree Kelvin or by 1 degree Celsius. So the relationship we have is uppercase C, which is heat capacity, is equal to M mass times lowercase c, which is specific heat capacity. And we will use that in the next 2 slides. Example 1. A 45 kilogram block of material requires 56 kilojoules of energy to increase its temperature by 1.0 degree Kelvin. Calculate its specific heat capacity. Now, this is uppercase C, it is its heat capacity. We know the mass is 45 kilogram, and we want to find lowercase c, the specific heat capacity. All right, so let's write what we are given. We know the heat capacity is 56 kilojoules, which is 56,000 joules. We know that its mass is 45 kilograms, and we want to find its specific heat capacity. The formula we have is uppercase C is equal to m times lowercase c. So heat capacity is equal to mass times specific heat capacity. We change that formula around to make lowercase c the subject, and we get specific heat capacity is equal to heat capacity divided by m. We substitute the numbers we are given, and we get 1,244.44 joules per kilogram per degree Kelvin. Now, we know that we cannot leave this with so many significant figures. So let's see, we have two significant figures here, and we have two here. So our answer can only have two significant figures. So we will have to round off at that position. And therefore, we get 1.2 kilojoules per kilogram per degree Kelvin. And that should be acceptable for CSEC. However, just to be on the safe side, we can also add plus or minus 0.05 to this answer to ensure that we know what our uncertainty is, just to play it safe. This is also correct, but CXC actually requires this format. We now look at question 2. You have 24.8 tons of water at 21 degrees Celsius in insulated tanks in your basement. What is the heat capacity of that water, given that the specific heat capacity of water, C, is 4,200 joules per kilogram per degree Celsius? So again, we write what we know. We know that the mass is 24.8 tons, and since it takes 1,000 kilograms to make a ton, we convert that to kilograms, and we get 24,800 kilograms. The specific heat capacity, we are told, is 4,200 joules per kilogram per day, and we want to find the heat capacity. So we know C, heat capacity, is equal to mass times specific heat capacity. Substitute the numbers we are given here, and we get this answer, and that would be joules per degree Celsius. Let's look at our significant figures. We have 3 significant figures here. We have 2 significant figures here. So our answer can only have 2 significant figures. So we'd have to round off at this position. And if we do that, we will get 100 megajoules per degree Celsius. But you see, in this, we don't know where is our uncertain digit and what is our uncertainty. And since we are rounding off here, then we will take half of that position, which is the tens position, and we will get 5. So our answer is 100 plus or minus 5 megajoules per degree Celsius. And this part here is to avoid any ambiguity. This here is also correct, but this is the format, this plus or minus format, that CXC requires. Now we look at question 3. And the question says, how much heat energy will be required to increase the temperature of a 45 kilogram block of metal from 25 degrees Celsius to 67 degrees Celsius if the specific heat capacity of that metal is 1,340 joules per kilogram per degree Celsius? Again, we write what we are given. And in this case, remember that a change in temperature in degrees Celsius is the same change in temperature in degrees Kelvin. So those two things are the same as long as we are dealing with change in temperature. So we know the mass, 45 kilograms. We know the change in temperature is 42 degrees Celsius when we subtract 25 from 67. We know that the specific heat capacity of this metal is 1,340 joules per kilogram per degree Celsius, and we want to find how much heat energy is required to do that increase in temperature of that particular mass of metal. Our formula says EH is equal to MC delta theta, that is this formula here, which is basically the same formula as that. We substitute the numbers we are given, 45 kilograms times 1,340 joules per kilogram per degree Celsius times 42, and we get this number here. Of course, we cannot leave that number like that because it has too many significant figures. 2 significant figures, 3 significant figures, 2 significant figures. Recall that for multiplication and division, our answer cannot have more significant figure than the factor with the least number of significant figures. And in this case, that will be 2, there or there. So we count 1, 2, and we have to round off at this point. So that would give us 2,500,000 joules. And since we are rounding off at this 100,000 position, we take half of that, which would be 50,000 joules. You can compress that answer as 2.5 plus or minus 0.05 megajoules, million joules. As I said, CXC requires this format. This is also correct. That was question 3. It requires 278 kilojoules of energy to increase the temperature of a 4.35 kilogram block of metal from 285 degrees Kelvin to 312 degrees Kelvin. Calculate the specific heat capacity of the metal. So let's write down what we are given. We know that the heat energy required is 278 kilojoules, and we need to convert that to joules because we cannot put kilojoules in this equation. We know that the mass is 4.35 kilograms, and that is already in the correct unit. We also know that the change in temperature is 27 degrees Kelvin. EH is equal to MC delta T. We make C the subject of the formula, and we get this. We now substitute. This is EH, that is M, and that is delta T. Put that in our calculator and we get this answer. But again, you know that we cannot leave this answer with that many significant figures. We have 3 significant figures here, 3 significant figures here, 2 significant figures here. So our answer can only have 2 significant figures. We will need to round off at that 3. And so you get 2,400 joules per kilogram per degree Kelvin. Just to make sure, since we are rounding off at this hundredths position, we take half of that, which would give us 50. And so the answer is 2,400 plus or minus 50 joules per kilogram per degree Kelvin. This is also correct, but this is the format we will write for CSEC. Now we come to derived formula. So far, we have been using this or that. How did we come up with this? Or where did that come from? Consider for a moment that if you take a hot piece of metal and immerse it in some water that is at room temperature, the metal will cool down while the water will heat up until they both achieve the same temperature. Assuming that no heat is lost, for example, to the environment, including the container, during this process, then the heat lost from the metal is the heat gained by the water, which brings us to the derived formula shown above, this one here. If we let sub 1 represents the metal, then EH of the metal will be M1 times C1 times delta theta 1. That's for the metal. And we let sub 2 represent the water, then EH for the water is M2 times C2 times delta theta 2. But remember that the heat lost by the metal is equal to the heat gained by the water. Therefore, M1 C1 delta theta 1 is equal to M2 C2 delta theta 2. That's how we came up with this derived equation here. And we will now use that. Now, this principle can be used to find the specific heat capacity of metals. And in a little while, we will see that with a little adjustment, we can also use it to find the specific heat capacity of liquids. And it is called the method of mixtures. So, question 5. A small piece of hot metal of mass 56 grams at 98 degrees Celsius is quickly submerged in 134 grams of water at 23 degrees Celsius. The water is gently stirred and the final temperature of both the water and the metal is 27 degrees Celsius. Recall, the metal will cool down, the water will heat up. Assuming that all the heat lost by the metal was absorbed by the water and that the specific heat capacity of the water is 4,200 joules per kilogram per degree Celsius, calculate the specific heat capacity of the metal. All right, so let's write down what we are given. If we let sub 1 represent the metal and sub 2, that is subscript 2, the water, then M1, which is the mass of the metal, is 56 grams. We carry that to kilograms. C1 is what we want to find, the specific heat capacity of the metal. We know delta theta 1, which is the change in temperature of the metal. It was at 98 degrees Celsius to begin with, and it cooled down to 27 degrees Celsius. So the change in temperature of the metal is 71 degrees Celsius. That's for the metal. Now for the water, which we will represent by the sub 2, the mass of the water is 134 grams, which is 0.134 kilogram. We are told what the specific heat capacity of the water is, and we know that the change in temperature of the water is 4 degrees Celsius. It was 23 to begin with, and once you put the hot metal in it, it heated up to 27 degrees Celsius. So the change in temperature of the water is 4 degrees Celsius. We said that M1C1 delta theta 1 is equal to M2C2 delta theta 2. We change the subject, or rather we make C1 the subject of the formula, which gives us M2C2 delta theta 2 divided by M1 delta theta 1. We know what these are, all 5 of these variables on the right hand side. And so we substitute. This is M2, C2, delta theta 2, M1, delta theta 1. Put all of that in our calculator and we get 566.197 joules per kilogram per degree Celsius. Let us check our significant figures. We have 3 significant figures here, 2 here, 1 here, 2 here, and 2 here. Just a reminder, for multiplication and division, our answer cannot have more significant figure than the factor with the least number of significant figures. And in this case, that will be this 4 here. So our answer can only have 1 significant figure. We have to round off here at that 5, which will give us 600. And since we are rounding up at the hundredths position, we take half of that position, which is 50. And so our answer is 600 plus or minus 50 joules per kilogram per degree Celsius. That is the specific heat capacity of the metal. This is also correct, but remember that's the format we will write for C-sec. Now that same principle can also be used to find the specific heat capacity of liquids by mixtures. Remember, you're mixing a metal. Technically, you're not really mixing, you're adding a metal, a hot metal, to a colder liquid. But we will call it method of mixtures. Question 6. A small piece of hot metal, so the metal is 56 grams and its temperature is 98 degrees Celsius, is quickly submerged in 134 grams of liquid. Now notice I didn't say water this time. A liquid, whatever that liquid may be, and the temperature of that liquid is 23 degrees Celsius. The liquid with the hot metal in it is gently stirred and the final temperature of both the liquid and the metal is recorded as 35 degrees Celsius. Assuming that all the heat lost by the metal was absorbed by the, and that the specific heat capacity of the metal is 907 joules per kilogram per degree Celsius, calculate the specific heat capacity of the liquid. Notice that in this case, it is very similar to the previous one, where we were finding the specific heat capacity of a metal, but in that case, we were using water here, and we knew the specific heat capacity of the water. In this case, we follow basically the same procedure, but we use that liquid here, not water, and we need to know the specific heat capacity of the metal. So this time we will let sub 1 represent the liquid and the subscript 2 represent the metal. So now we know the mass of the liquid, it is 134 grams. We are given that. We want to find the specific heat capacity of the liquid. What is the change in temperature of the liquid? Well, it was 23 degrees to begin with, and when we put the hot metal in it, it increased to 35 degrees, so the difference is 12 degrees Celsius. So that is for the liquid. For the metal, we know the mass of the metal converted to kilogram. We know the specific heat capacity of the metal, and we know the change in temperature of the metal. It was 98 degrees to begin with. You put it in the liquid, and its temperature dropped to 35 degrees. So the change in temperature of the metal is 63 degrees Celsius. Okay, we have our formula here. M1 C1 delta theta 1 is equal to M2 C2 delta theta 2. We ensure that C1 is the subject of the formula, and just like we did before, C1 is equal to M2 C2 delta theta 2 divided by M1 delta theta 1. Substitute our numbers, work that out, and we get this 1989.985 joules per kilogram per degree Celsius. Again, let us check our significant figures. We have too many significant figures here. the numbers we have been working with, that is two significant figures. This one is 3, this one is 2, this one is 3, this one here is 2. So our answer can only have two significant figures. We will have to round off at this point. So we get 2000, and because we are rounding off at the hundredths position, we take half of that hundredths position, which is 50, and so our uncertainty is plus or minus 50 joules per kilogram per degree Celsius. So we will write this as our answer for the specific heat capacity of that liquid. As I said, this is also correct, but this is now in standard form, but we will stick with that one. Now finally, if you add some hot liquid to some of the same liquid at a lower temperature, how will you find the final temperature of the mixture, especially that you will not be given the specific heat capacity of the liquid? So let us say that you add 2.45 kilograms of hot water at 98 degrees Celsius to an insulated container which has 7.84 kilograms of water at 11 degrees Celsius. So you're adding a little bit of hot water to a larger quantity of colder water. What was the final temperature of the water immediately on mixing them? Assume that no heat is lost from the water. So let us see what we are given. Let the sub 1 represent the hot water, and the subscript 2 represent the cold water, and let y represent the final temperature, because we don't know what that is, and therefore we cannot find a change in temperature. So we know that M1, which is the mass of the hot water, is 2.45 kilograms. That is in the right unit. Well, we aren't given the specific heat capacity of the water. We are not given the change in temperature of the hot water either. But we know that it was 98 degrees Celsius and it dropped to y degrees Celsius. So the change in temperature will be 98 minus y. For the cold water, the mass is 7.84 kilograms. We don't know the specific heat capacity either, but since it is water, then those two are the same. We also know that the change in temperature of the water, well, it was 11 degrees Celsius to begin with, and once you put the hot water in it, it heated up to y degrees Celsius. So the change in temperature is y minus 11. We will work with those values. So we have two unknowns. We really want to find y, we want to find the final temperature. This specific heat capacity of the water will not pose a problem because, as you will see, specific heat capacity on this side and specific heat capacity on that side, they are the same. So we will just cross them out. So what we are left with is the mass of the hot water times its change is equal to mass of the cold water times its change in temperature. Now we have a simple equation here. We work that out. We get 240.1 kilogram per degree minus 2.45 y kilogram, and so on. We solve that. We solve it. And we eventually come up with y is equal to 31.71. Again, let's look at our significant figures that we are working with. 3 significant figures, 3 significant figures, 2 significant figures, and 2 significant figures. So our answer can only have 2 significant figures. We round off at that ones position and we get 32, and since we are rounding off at the ones position, we take half of that, which would give us 0.5. So our answer is 32 plus or minus 0.5 degrees Celsius. That is the final temperature when you added this hot water to that colder water. Or you could say 32 degrees Celsius, correct two significant figures. But remember, this is the format that we will write for CSEC. It is good to check your answer to see if it is reasonable. Now, if we say that the final temperature is 31.7 degrees Celsius, if we say that, we subtract 31.7 from 98 and we get 66.3. We multiply that by the mass and we get this amount. If we do the same thing for the water, the colder water, we subtract 11 from 31.7 and we get 20.7. We multiply that by this mass. Notice that we get the same answer here. So we know that our 31.7 degrees Celsius final temperature is correct. So we just completed this formula here, this one, formula 6. As of now, formulae 1, 2, 3, 4, 5, 6, all of those have been completed. And in the next video, we will consider formula 7 and its variation. Now, just to make sure we understand this, we were using formula 6 to find specific heat capacity of a solid or a liquid using the method of mixtures. In formula 7, we will be finding the specific heat capacity of solids or liquids using an electrical method.